Hi all, welcome back to Cracking the Fang Interviews. Today we are going to be talking about a very fresh problem, and this problem mostly applies to people who are in the field of AI and ML and even data science. And this is something we used in our day to day during training, which is dot product operations. And the problem is asking you to particularly think about an implementation of dot product of two vectors, but these are sparse vectors. So just to set the tone here and clear the terms, what do we mean by sparse vector? So let's say we have a vector v1, and v1 is nothing but a collection of scalars. That's how you could think about it. And scalars are just numerics. It could be floating points or integers. And suppose v1 is a vector and the value across dimension 0 is 1, value across dimension 1 is 2, and value across dimension 3 is 1. What do we mean by a sparse vector? Now imagine v1 to be a vector of maybe 1000 dimensions. We saw a vector with 3 dimensions. I'm scaling it up to 1000, and it would only have maybe one set at index 99. But sparse vectors don't require you to just have one set. They're not supposed to be exclusively one hot vectors. These are one hot vectors when you just have one set at one position, one dimension of the vector. Another example to make the idea more concrete could be a sparse vector which could have maybe 1.2 and 1.8 set, but only two dimensions have certain values. And the challenge here is the computation. Given you have these huge sparse vectors, this could be in millions of dimension. The compute complexity scales as a power of O of D in this case. And this is just talking about one vector. The question is asking you to perform a dot product of two of these vectors. And typically in multiplication, the complexity is around O of n into m, right? So let's see how we can, think about implementing this and solving the problem with an example. So here I have a concrete example where the first index can be thought of as the dimension, and the second index is the value at the dimension. What this means is v1 is a vector. At index 0 its value is 1, at index 2 its value is 3, at index 3 its value is 4, and v2 is a vector. At index 2 its value is 1, index 3 its value is 9. The rest are zeros. Same with this. And what you need to do is compute dot product. So what this would mean is v1 dot v2 could be mathematically represented as, suppose these are n-dimensional vectors. I would say I is 1 to n, v1 of I multiplied by, again these are scalars, v2 of I. So you'd go through each dimension and multiply them, right? So the complexity would be O of n. Or if you're since you've assumed n dimensions, the complexity is O of n. You'll be doing n amount of work depending on the size of the vector. This is fair. This is a good algorithm to start off with, but is there a way to do better? Do you actually need to go through all of these n dimensions is the question. Let's look at one approach here. The first approach would be, you're given these two arrays here. So you essentially need to first go and understand what indexes are in them, right? So you might not be able to implement a O of n algorithm right away given you don't know the mapping here. I'm not assuming you have access to a dictionary structure. So let's see how we solve the problem with respect to the given data. The first approach here would be, you take the smaller array. In this example, it's V2. It only has two elements set. I would also call it the sparse array. And you use binary search to check if the same index is present in the other array. If it is, then you just multiply those values and do summation over all the indexes. And the time complexity here would be n times log of m, where n is the size of the smaller array and m is the size of the larger array. So what I mean by this approach is you essentially pick the larger array, which is m, v1 in this case, and you pick the smaller array, which is n, of size n. The dimensionality of both is essentially the same, but the size of the arrays are different. And you pick each element in this array and you go and perform binary search in the bigger array. So what you're doing here essentially is scaling this, or I would say reducing the time complexity of doing a linear search for each element from v2 into v1 from O of m to O of log m. The reason you're able to do that is binary search, which reduces the problem space by half. So at every point in time, if this is your search space m, it's gonna break it down into m by 2 in the next step. And again, we are assuming m is sorted. That's a given. And it's gonna further break down into m by 4, so on until the size is 1, where the time complexity of this becomes log of m. So this is one fair way of solving it. Without using any space complexity, we are assuming there's no extra space being used in this problem, and you get 2 of n into log m. Now there's another approach that I'd like to talk about, which is we can make use of a particular data structure to go from O of n log m to O of, I would say, n, or sorry, m in this case, because m is larger. Let's see how we can do that. So this is the time complexity. Again, as a thumb rule, whenever you're trying to make something faster in terms of time complexity, you trade it with space complexity. So here the space complexity is none, and here there would be some space complexity. Let's see how we do that. So again, we have two arrays v1 and v2, and we have the index and value pair, as I mentioned in the previous slides. We have these pairs. And what we are trying to do is, what we could do is go through v1 and make a hash table for v1 and just go and mark those particular indexes, say index 1 with their values, 2.1, index 3 is 4, index 5 is 7. I've just made up values to show for representation. You do the same for v2. For example, index 3 is 2, index 8 is 5. So essentially two indexes here, 3 indexes here and 2 indexes here. And now what you can do is use something like a default dictionary in Python, which the property of default dictionary, just a quick recap, is when you look for a value for an element, for example, if you look for 4 in v2, it's going to return the value 0. So everything which is not set is going to have a default value. That's why it's called a default dictionary. And what I would do here is pick the smaller array, right? Pick the smaller vector, which is v2 in this case, and iterate through. For an example, I write some code here for key comma values in v2.items. Again, I'm writing Python code, but this can be used across different programming languages. And if v1 of that key is not equal to 0, so it's gonna pick 3 and it's gonna go look for 3 in v1. And if it's not equal to 0, it's gonna say and I'm gonna initialize a dot product. It's gonna say dot prod plus equals to v1 of key into v2 of key. So what is the time complexity of this approach? Again, this is of size m, the bigger one, and this is of size n, the smaller one. What we are essentially doing is just looking at the values which are set in our hash table and checking them against the bigger vector. So the time complexity of this for loop is going to be O of n. That's even better than what we thought, which is O of m, the bigger array. Since we are using the smaller array here and trying to be smart with sparsity, because anything that's not present in either of these arrays will have a zero contribution to the dot product. So there's no use of checking more. Checking less is important. You're sort of doing a intersection. By that I mean this is how the intersection of these two sets will look like. So you don't need to really check anything else. And again, now you've made a trade-off here. You've created these two additional data structures. So the space complexity will be something like n plus m. I hope the concept was clear, and thank you so much for following Cracking the Fang interviews. Please like, share, and subscribe to the channel for more exclusive content.